Hello everyone, welcome to this lecture on electromagnetic induction. In today's class we will talk about a very new concept that's called self-induction. So self-inductance is a process in which an electric current it self-induces its own counterpart basically. So when a current flows through a coil, the magnetic field is set up in it. That is something that we know. If the current passing through the coil is changed, the total magnetic flux linked with the coil changes and an EMF is induced in the circuit. So just have a look at this side figure. There is a current. By the way, there is a field or there is a voltage source which is basically providing this current. For the time being, let's not bother about whether this is an DC or an AC source, just a kind of a voltage source which is providing you this current. The current is going through this coil, and because of which there is a magnetic flux linked with the coil that is changing. I mean, basically the current is producing, since the current is going in a circular fashion surrounding this particular loop. That is the reason why we are getting a magnetic field. Now if the current changes, if you either increase or decrease the current, electric current, in that case the magnetic flux linked with this coil will also change, and as a consequence there will be an EMF induced in this coil. And the question is, what is the direction of that EMF? The direction of the EMF will be such that the induced current, which will be because of the induced EMF, that will oppose the flow of this current. So it is as if you are increasing this current I, because of which the magnetic flux linked with the coil is changing, and because of which there is an EMF. So that EMF will be generated in such a direction that the resulting current because of that EMF will oppose the increase in this original current. Alright. So how do we define self-inductance? The property of electric circuit by virtue of which any change in the magnetic flux linked with it induces an EMF is called self-inductance or self-induction. So self-induction opposes the growth of current in a circuit when the switch is on, and also it opposes the decay of the current when the switch is off. So that means whenever the current is increasing in a circuit, the self-induced current will oppose that. It will not allow the electric current to increase further. Similarly, when the electric current is decreasing, when electric current will decrease whenever we switch off the circuit. So if there is no coil, it is just a linear kind of a circuit. In that case, what will happen? Whenever we will switch off the current will instantaneously go down to zero. But in this case, because of the self-induction, the current will not go off to zero instantaneously. The self-induced current will oppose the decrement of the current also. So self-induced current keeps on changing its direction based on whether the original current is increasing or decreasing. So in the next few slides we will talk about the direction of the induced current. But before that, let's consider that there is a coil which has got N turns and it is carrying a current I. So we are going to basically find an expression of the self-induced coefficient of self-induction, or rather we are going to make a definition of the coefficient of self-induction. So if you have a coil which is having n numbers of turns and it is carrying a current I, this is by the way original current which is coming from some kind of source. In that case, what we can see, we can write phi is directly proportional to I. Now what is phi? Phi is the total magnetic flux linked with the coil. Actually, although I am saying in this case say phi, sometimes people may like to write a phi b kind of a thing, say for example b for magnetic flux. So anyway, not an issue. So phi is directly proportional to I. By the way, why it is directly proportional? Because whenever the current, original current basically, this capital I is increasing, then the magnetic flux linked with the coil is also increasing. So that is why there is a direct relationship. So if we know that whenever there is a proportional sign, if we have to remove it, we'll have to put a constant of proportionality. So let's in this case call it to be L, and derive on take a derivative on both the sides with t, that is time. In that case, we get d phi dt, that's equal to L di dt. Because L is a constant of proportionality, no need to make a derivative with respect to time. But current will definitely change with time, so we are taking a derivative of the current. Now, what Faraday's law says is that whenever magnetic flux linked with a coil changes, there is an induced EMF, and that is given by E is equal to minus of d phi dt. Or rather, we can write d phi dt, that's equal to minus of E. The same thing I have directly put over here. In place of d phi dt, there is minus E, which is equal to L di dt, or E is equal to minus L di dt. So this is the ultimate expression that we get. So here L is a constant known as the coefficient of self-induction. Now if di dt is equal to 1, that means if the rate of flow of current through the circuit is 1, that means 1 ampere current flows in 1 second. If that is what is the relation, in that case we can say that E is equal to minus of L. So from here we can make a statement, or rather make a definition of the coefficient of self-induction. So the coefficient of self-induction of a circuit is defined as the EMF generated when the circuit has got a current flow rate of unity. That means the current flows with at a rate of unity. In that case, whatever be the EMF generated in the circuit, that is it's nothing but the coefficient of self-induction. That's what is the magnitude wise value. All right. Well, now there is a physical significance of this also. What is the physical significance? It is very important. The self-induction or self-inductance, it plays the same role as the mass or the inertia, moment of inertia basically in mechanical motion. Now, in mechanical motion, we know that suppose there is a body, there is an object which is of 5 kg, 5 kilogram, and another body which is of 2 kilogram. Now, given a constant amount of force, this 2 kilogram will move easily as compared to this 5 kilogram. Or rather, if I have to say that amount of force required to move this 2 kilogram will be less than as compared to 5 kilograms. So that means since the mass of this particular body is higher, it has got higher inertia towards the motion. It doesn't want to be in motion. Quite similar to that, you have got moment of inertia, which is an inertia related in the related for the case of rotational motion. So you have rotational inertia, which is the moment of inertia, we call it. Self-induction plays the same role as the mass or the moment of inertia in mechanical motion. That means in an electrical sense, as current wants to increase in a circuit, because of self-inductance, there is an induced current which opposes this growth of the current. So you can have this particular picture where the circuit is closed, that is key is pressed. So the current increases gradually. Suppose this particular source is not a constant source, rather it gives you a variable current which increases with time. In that case, what will happen? Because of the increment of current, original current I, the magnetic flux linked with this coil will keep on changing. That means that will also increase because phi is directly proportional to I. So as the magnetic flux increases, the induced EMF also increases, and finally that gives you an induced current. But induced current must come in a direction which is opposite to the original direction. See, the original direction of the current is this, induced current is in opposite direction. So that means induced EMF is created in this fashion. This is plus, this is minus, suppose. That means induced EMF is opposing the original EMF or original potential difference of the circuit. Got it? So the induced current is responsible for slowing down the growth of the original current. Quite similar to this, whenever the circuit is off, the circuit key is open. In that case, the current I sharply falls off to 0. However, because of the induced current, now induced current doesn't allow this particular phenomena to happen. That means it doesn't allow the current to fall off to 0. In this case, induced EMF makes a supportive role. That means induced EMF will be in the same direction as the original EMF in the circuit, and it will allow the current to flow in the same direction. So induced current and the original current will have the same direction. So suppose this is time and this is the original current I, and I make a profile like this. That means in half of the time t by 2 the current increases and half of the time current decreases. In that case, in the first half the induced EMF will be in opposite direction to the original current, and in the second half the induced EMF will be in the same direction of the original current. So that is why in the second half it will play a supportive role, in the first half it will play a negative role or opposing role. So that is why whenever I increases, induced current opposes this motion, and whenever I decreases, induced current supports the motion. So that is why it sort of gives you an inertia in the sense that it neither wants to increase the current nor wants to decrease the current. So that's a kind of inertia, electrical inertia, we can say that is why we say that self-inductance that plays the same role as mass or the moment of inertia in mechanical motion, right? It has got the same role, almost similar role. So that's what is the physical significance, that it is nothing but an electrical inertia. Self-inductance is an electrical inertia. All right. So let's now consider the self-inductance of a long solenoid. Solenoid is basically what? Solenoid is a wire basically that you wound around a core. But for this case, let us consider that the core is made of air only. That means we do not put any material media inside. This is just air. So in this case, if we have n numbers of turns of this coil, and let's say the length of this solenoid be L, and say area of cross section be A. In that case, what is the magnetic field in the central line of this solenoid? That's given by this expression, B is equal to mu naught Ni upon L. So I is the basically current which is flowing through it. So this is the current I which is flowing through it. Mu naught is the permeability of free space. Now if A be the area of each turn, then the magnetic flux linked with each turn is phi is equal to B into A. Now in this case, an important consideration is flux. Normally we know that flux is equal to dot product of B and A, but in this case I am not considering any dot product. Why? Because I have considered the direction of this magnetic field and the area vector is same. They are making a 0-degree angle. Basically I am considering one single loop. Let's consider this loop, one single turn. So area vector and magnetic field, if both are in the same direction, in that case theta between them is 0. So I can write BA cos of 0-degree, cos 0 is 1. So it is just like BA. So that is why we have directly written BA. So phi is equal to, in place of B, replace mu naught Ni upon L. So we get this expression. Now therefore, the total magnetic flux linked with the whole solenoid. Now previously what we have encountered, this phi is nothing but the flux through one single turn. If this is the solenoid, this is one single turn, this is another turn, this is another turn. So I am talking about one single turn through which the magnetic flux is this much. Now if there are n turns, then what will be the magnetic flux? Phi B is equal to n multiplied by phi, and ultimately that is mu naught n square Ia upon L. So applying Faraday's law, we can easily get E is equal to minus d phi B upon dt. So everything is a constant except for I, which keeps on changing with time. So we take everything else outside and make a derivative of I with t. Again, from the definition of self-inductance, we get E, the induced EMF, is equal to minus L di upon dt. So comparing these two equations, we can get L to be is equal to this quantity, mu naught n square A upon L. So this is the expression of self-inductance of a long solenoid. So if you are given the area of a solenoid, if you know the length of a solenoid, number of turns of a solenoid, you can easily get the value of the self-inductance of that solenoid, which will remain a constant for that particular solenoid. So by the way, there is one important point to make here, that the SI unit of self-inductance is Henry. So this is very important to remember. All right. So that's all I have for today. We have talked about self-inductance of a solenoid. We have talked about the very basic concept of self-induction. In next class, we will come up with mutual induction. and reciprocity theorem if possible. And we will try to understand the relation between self-inductance and mutual inductance, or rather we will also learn to distinguish self-inductance from mutual induction. All right, so thank you for today. Thank you so much.